Hello and welcome. I'm going to go over some examples on equivalent system and how to simplify systems. I'm going to start with a 2D problem, kind of a simpler problem, again to warm up. So for the 2D force system shown, find the equivalent resultant force and couple moment acting at point A, and then a single force location measured from A. All right. So what the problem is asking is replace these three forces by one force at point A. And since we are moving the forces to point A, we are going to create some moment. What is that moment? And then later it asks us that, hey, can you get rid of that moment? Just replace it by one single force, which requires to be at a certain location measured from point A. So basically, this is my beam, this is my point A, this is my beam, my point A. Part 1 says a resultant force Fr and a resultant moment, and then later it says an Fr at a direction that I don't know and at a distance. Okay, so this is what the problem is asking us. The equation that we have for Fr is summation of all forces, and the equation that we have for moment is summation of all couples moment, existing ones, plus summation of, in this case, all FDs, moment about point A. These are all FDs. So this is existing, this is generated, rated because we moved forces to point A. So let's go one by one. Let's go finding Fr first. So Fr, we have three forces. Summation of forces in X, summation of forces in Y. This is what that means. So if I add all my forces in X direction together and all forces in Y direction, I can find my Fr. So let's see. This force, the 50 pound at the end, the X component of it is going to be 50 pounds cosine, or excuse me, sine 30. And the Y component of it is going to be 50 cosine 30 pounds. The other force that I have, 100. So there is a vertical component or Y component of it, which is going to be 100 pounds, 4 over 5. And then, of course, there is an X component, which is going to be 103 over 5 pounds. Okay. So sigma Fx, all of them together. The first force, 200 pound, doesn't have any X component. The second one has 100, 3 over 5, and it's plus. If going to the right is my plus X, going up is my plus Y. This last force that I have, plus 50 sine 30, all of them have unit of pound. This will be 85 pounds in x direction. I'll do the same thing for sigma Fy. If pointing up being positive, the first one is plus 200 pounds. The second one is pointing down, minus 100, 4 over 5. And the last one is pointing up again, plus 50 cosine 30. All of them in pounds. This will result in 163.3 pounds. These are important numbers. We're going to get back to them. So my FR, in other words, is going to be 85I plus 163.3 J. That is my FR. If I want to find the magnitude of FR, all I have to do is 85 squared plus 163.3 squared, square root of that, which is going to give me 184 pounds. Okay. One other thing that I can do is find the angle that FR is making. The y component is 163.3, the x component is 85, so tangent of that angle is going to be 163.3 over 85. This theta is going to be 62.25. So I found the magnitude, I found the vector format, I found the angle. I don't think there's anything else to find about this force. So this force, we found it to be, I'm just going to write the magnitude here, 184 pounds. 184 pounds. Okay. First part is asking us, hey, what about moment? Because we moved forces to point A, right? I don't see any existing couples moment here. So this existing goes to 0. And because I'm moving each force to the point A, it is going to create a moment about point A. So let's find what is that moment. I'm going to take this rotation direction to be positive. So whatever rotates counterclockwise, I'm going to put a plus next to it. Let's just start with the first force. Is 200, and the perpendicular distance between point A and line of action of that force is 3 feet. So it's 200 pound. Perpendicular distance is 3 feet. And if I pin at point A, my force is trying to rotate the beam counterclockwise, which agrees with my sign, so it's going to be plus. So I'm going to leave it at that. Next, let's go to the 100-pound force. I have already resolved it into two components. Okay. One of the two components, which goes through point A, doesn't create any moment. Or in other words, the perpendicular distance between point A and the horizontal or x component of that force is 0. So I'm not going to write it here because it's going to make it busy. The vertical component, however, it doesn't go through point A, so it is going to have a moment. So the perpendicular distance between point A and that component is 3 plus 3, 6 feet. Now let's see the rotation. Pin at point A, this vertical component of that 100-pound force is trying to rotate my beam this way, which is against my sign. So I'm going to put a negative next to it. Let's go to the last force that I have, the 50 pound. Again, the horizontal component, the x component, goes through point A. So the distance between point A and line of action of that horizontal force is 0, so I'm not going to write it. The vertical component, however, which is 50 cosine 30, has a distance to point A of 3 plus 3 plus 3. If I pin at point A, the force that's pointing up, trying to rotate my beam counterclockwise, so that's going to be plus. So my magnitude of my moment is going to be 509.7 pound-foot. I got a positive number, so that means it goes with my sign, so it's rotating this way, or rotating counterclockwise. Both of them are acceptable. This is the direction of rotation. So this moment, which I drew it, when I drew the figure up there, I didn't know which way it's rotating, so that's why I just put a random rotation on it, but in reality it's going counterclockwise. So now let's look at the second part of this problem, which says, hey, replace this with a single force measured from point A. So let's clear this slide. So so far I got my FR 85I plus 163.3 J with an angle of 62.5, something like this. 163.3, 85, 62.5. Okay, this is my FR. So now I want to move this force from point A. So remember, when I have force F and move it to point A, because it's not on its line of action, it's going to generate a moment for me. So now if I have a force, so from case 1 we're going to case 2. This means move it to point A. So now if I have case 2, I want to go to case 1, which is what I have here. I have a force, I have a moment. By the way, I found it to be 509.7. Let's just call it 510. And it says, hey, move it away and find that distance for me. So M equals FD when D is perpendicular distance between point A and force. Then I can say D, that perpendicular distance, equals moment at A divided by F. Remind me again, what was magnitude of FR? 184 pounds, magnitude of it. So if I divide my moment about A, which is 510, by 184 pounds, I get a value of 2.77 feet. But you gotta pay attention. This is perpendicular distance between A and FR. So let me draw my beam here. This is point A. My FR, which I have it up here, is like this. So the distance that I found is perpendicular distance between A and FR. So the distance that you just found is this distance, 2.77 feet. You got to pay attention. This is the perpendicular distance that we just found. So now my question is, someone might ask, hey, what can you find this distance for me? This is what I'm interested in. So the answer to that is yes. The way you gotta do it, you have to find the distance between that FRY and point A. So if I want to find that distance, I have to use my moment divided by the vertical component. And that will give me 3.12 feet from A. And that is the distance between point A and vertical component of FR. So this is an important point that you got to pay attention when you do the division to find the distance. That is always the perpendicular distance. Here also is perpendicular distance between A and 163.3. This was the vertical distance between A and force FR, the total force FR. So that distance that you find is always perpendicular distance between the point and whatever that you are measuring. Let's look at another one. So problem like this says, for the forces and couple moments applied to the pipe, find the equivalent. Find equivalent resultant force and couple moment at point O. Okay, so that means move everything to point O. Give me an FR and give me an MR. That's all I care about. Get rid of all of these forces, all of these moments, and everything that is there. So let me remind one more time. FR is summation of all forces. Here I have 1, 2, 3. So it's basically F1, F2, F3, all in vector form. So let's get to work. Let's do this one first. Force F1 in a vector format. I know the magnitude, which is 300, and I know the direction of it. It's pointing towards plus z-axis. So that would be K, 300 K. 300 Newton K or 300 K newtons. Let's look at F2. F2, the magnitude is 200 and it is pointing towards X and Z. So I am going to draw another eye here. If I'm looking at this way, I'm going to see X-axis, Z-axis, and I'm going to see F2 pointing down with a degree of 45. F2 has the magnitude of 200. So the Z component of it is going to be 200 cosine 45 I. The Z component of it, it's going to be minus 200 sine 45. And that is K. And finally, F3, I have the magnitude of it, and it's pointing towards positive y-axis. So it's 100 Newton, and it's in the direction of J. So I think I have enough information that I can just find FR. So FR is just summation of all of that. That means all the I's together, all the J's together, and all the K's together. So for the I have 141.4 I plus 100J plus 300K and minus 141.4 K. And all of these have units of Newton. So my FR is going to be 141.4 I, 100 J, and plus 159 K with the units of Newton. That's my FR. So force was easy, and usually that is the case. Now let's look at moment. So let me change the pen here. So moment, the equation that I have, MR is summation of existing couples moment plus summation of R cross A, F's. That position vector is from from O. We're trying to move everything to point O to line of action of F. So this is the first one is existing. The second one is because we're moving the forces to point O, we are going to create some moment. So let's see. We have two existing couples moment. We have one existing couples moment, which I'm going to write it right there on the figure. MC1 is the same as F1, or the direction is same as F1. So the magnitude is 100 Newton meters, and the direction is plus Z. So that's 100 K Newton meters. MC2, moment of couple 2, is 180 Newton meters, but the direction is same as F2. Okay, so that means 180 Newton meters. So my MC2, I'm going to write it right here on the figure 2, is going to be 180 cosine 45I minus sine 45J Newton meters. Okay, that's my existing. I'm going to move three forces to point O. So I'm going to create three moments. I need three position vectors. All starts from O, goes to the point, to the line of action of force. So for the first one, I start from point O, I go to the line of action of F1. I'm going to call it R1. So let's figure out what is R1. R1 is from O to A. How much I'm moving? I'm moving 0.5 meters. In what direction? I'm moving in Y direction. So it is 0.5 meters J. R2 goes from point O to line of action of this force, which I can take point B for it. I'm just going to draw it on there, but they're kind of overlapping. So my R2 is going from point O to line of action of force F2, which is point B. How much I'm moving? 1.1 meters. Which direction I'm moving? In J direction. R3 is between point O and line of action of force 3. So look on the figure. This is the line of action of force 3, and point O is on it. So it's basically position vector between O and O, which is 0. I'm going to add an arrow so I know it's in vector format. So I think I'm ready to kind of write everything in vector format. I'm going to go to the next page. So my moment was summation of MC's, existing, summation of all r cross f's, all vector, vector plus vector. So MC1 was 100k units of Newton meters. MC2 was 127.3 I minus 127.3 K Newton meters. So these are my MCs. And then I have two R cross Fs to write, which I'm going to write them here. R cross F, it's a vector. I have to have ijk in it. ijk. R1, I found it to be 0.5j, so it's 0.50 meters. And F of 1, I found it to be 300k units are newtons. Okay, plus I have an R2 and I have an F2. It's a vector, so I need ijk to be in it. R2, I found it to be 1.1j. Remember, you do not put ijk anywhere else. All we care about are the components now. And F2, I found it to be 141.4 I, 0j minus 141.4 k, which is newtons. So if you do the math on this one and then add all i's together, add all j's together, add all k's together, we are going to get 122i minus 183k Newton meters. This is a moment that is located only in x and z plane. So the moment, the z is actually minus, x is positive. So if I want to draw kind of what MR looks like this, and then my FR, summation of my forces, had all ijk in it and they were all positive, so it's kind of like this. That is my FR. I moved everything to point O and I kind of simplified this problem. Okay. All right, let's look at another problem. So this problem says replace the three forces acting on a rigid pipe frame by their equivalent force R acting at point O and a couple MO. So what the problem is asking us is, please take this pipe, take all the forces and replace them by 1 FR, whichever it's going. I'm just going to put it at a random direction. It's kind of obvious, but I want to just put it at random direction. So this is what the problem is asking us. Replace it by 1 FR and 1 MR. So let's do FR first. So the resultant force is summation of forces in vector format. I have three forces, so let's call this F3. Let's just start with F1. F1 in vector format has a magnitude of 80 newtons and it's pointing towards plus z, so that's going to be plus k for me. F2 has the same magnitude and it's pointing towards minus z or negative z, so that's going to be minus k for me. F3 has the magnitude of 180 Newton and is pointing towards minus z, so that's also minus k. So now going back to my equation, I have to say 80k minus 80k minus 180k, all with units of Newton, will result in minus 180k with units of Newton. Okay, so that's my FR. For a moment, let me use a different color. So for a moment, the equation that I have is summation of all couples moment plus summation of all R cross F's. Okay, this is existing. This is because of moving forces to here is point O. Okay, so I look on the figure. Do I have any existing couple? It might not look like it at the beginning, but if I look at these two forces, F1 and F2, these two are parallel, opposite direction, same magnitude, and they're separated by a distance which is 0.75 meters. So those two are forming a couple. So yes, there's an existing couple, which to find the magnitude of it, or the vector format of it, I have to do R cross F, which is different than the second R cross F, and I'm going to explain in a minute. For a couple, this is moment of a couple. Position vector starts from line of action of one of the forces to line of action of second force, or this one that I'm going to write there. For this problem, I'm going to start from this point and move this much, so I'm going to call that R1. Okay, and then because I arrive at force F1, I have to use force F1. So let's figure out what this is. This is a vector, so I need ijk. The second row is going to be R1. Let's figure out what is R1. R1 is moving how much? 0.75, and that is on plus x direction, so 0, 0. Force F1, I just figured it out. It's 80 Newton in the direction of K. This one is meters, this one is newtons. So that's my existing moment. But I also have an R cross F because I'm moving. So I took care of these two. I don't need to worry about them anymore. But I still have one force that I'm moving to point A. And because I'm moving it, it is going to create a moment. And that moment is R cross F. The R here is different. The R is from O to line of action of, in this case, F3. So I start from point O, I draw a position vector, and I arrive at F3. So this one, it's an I, J, and K. Second row is going to be R, which starts from O, goes to the line of action of F, which I'm moving 1.25 meters, 0 and 0 units of meters. And my F3, which I already have, it's 0, 0 and minus 180 Newton. So these two are going to be added together, and the first one is going to result in minus 60J Newton meters. The second one is going to result in 225J Newton meters. So my MR is going to be plus 165J Newton meters, and that is my MR and FR. The directions that I put them on, the first, I had no idea. I just put them at a random direction. So let me correct that figure and try to put correct forces on there. So my FR is pointing down, so it's going to be minus 180. The minus is redundant because I'm pointing down, but anyways. And my moment is going to be in J direction, so my moment is going to be 165 Newton meters. And in order to just kind of remember that that's the moment, I'm going to put a rotation on this problem too. Okay, let's look at another similar problem. Replace the loading shown by a force and couple system at point O. So we are moving everything to point O. Force, summation of all forces in vector format, which how many do I have? Let me label them. This is going to call F1. This one I'm going to call it F2. So F1 is a 40 pounds. Which way it's pointing? It's pointing towards minus Y. So minus J. Force F2 is in X and Z plane. I'm going to draw a beautiful eye, and I'm going to look at it this way. So what I see is X, Z, and a force that is kind of like that. Okay. I know it's behind the axis, but it really doesn't matter at this point. This angle is 30. So the X component is 80 sine 30. And that's I. The Z component, because it's pointing towards negative Z, is going to be 80 cosine 30, and in the direction of K, the units for it is pounds. And that's the two forces I have. So the summation of the forces is going to be minus 40J plus my second force, which is 80 sine 30 I minus 80 cosine 30 K, which it will result in 40I minus 40J minus 69.2 K, and that is in pounds. Alright, that was forces, which is usually easier. So now let's look at the moment. Moment again is couple summation of R cross F's. I'm going to skip the explanation. One is existing, one is because we're moving. The existing, I do have an existing moment. The magnitude of it is 60 foot-pounds. But what is the direction of it? So the rotation that you're seeing on the figure is direction of rotation, and it's not the direction of moment. Moment is a vector. So what I'm going to be doing is using right hand rule. So fingers are going to be curled in the direction of rotation, and your thumb is going to point towards the direction of the moment. So if the direction of moment is this way, that is minus Y. So that is minus J. That is how you figure out the direction of moment. But also, we're moving two forces. We're moving F1 and F2 to point O. So the position vector is from O to line of action of each force, F1 and F2, plus It's a vector, so I need ijk. Position vector from O to F1. How much I'm moving? 12 inches. And in which direction? In positive z direction. F1, I found it to be minus 40J. So pounds, inch. That's because I move force F1 to point O. The second one is going to be F2. From point O, position vector to line of action. Whatever you want to call that point. Point A, point B. I just got to figure out how much I'm moving from point O. I'm moving, so let's put ijk here. It's a vector. I need the ijk. I'm moving minus 15 in x direction, minus 10 in y direction, plus 12 in z direction. I get inches. F2, I already have it. I have 40 I, 0J minus 69.2 pounds. That's all I have. I have an existing MC, then I'm moving two forces. So if you do the math on this one, you are going to get 1172I, 162J, 400K pound inch. You know, those numbers are too large, too big. I'm going to divide it by 12. 98 I, it just looked a little bit better. 13.5 J, 33.3 K. That makes it pound feet. They're both correct. They're both acceptable in this regard. Okay, let's look at another problem, the last one. Find the resultant couple moment and a stated in Cartesian notation. Okay. Resultant couple moment. So if you look at this problem, it doesn't tell you to find the force pointing at point O or point C or move it there. Because if you look carefully at the figure, you see two couples. You see these two. They are parallel, same magnitude, opposite direction, at a distance. And then I see these two. Same magnitude, opposite direction, parallel, at a distance. So what we have here is summation of couples moment. Plus, there is no R cross F. There's no other force to move. No other force other than couples. So all I have to do is find those two couples moment. Let's call them couple 1, couple 2. MC1. Remember, this is a vector. This is R cross F. R1, F1. So the distance between them, doesn't matter which one you start with. I like to start from the bottom one, go up, because my R then is going to be positive. So this is a vector, so I need an ijk. Second row is my R1. How much I'm moving? I am moving, let me see, this is 4, this is 2. I'm moving 2 meters in J direction. That's all I care about. 2 meters in J direction. I arrive at this force, so I got to use that 300. That's 300 pointing towards positive X. That's all I care about. That's my couple 1. Moment of couple 2. R2 cross F2. Let's still go up. So this is going to be my R2. I start from A, arrive at point B. Oh, I didn't even notice. So this is going to be AB. R1 was BC. And then I use F at point C. So I arrive at point B, so I'm going to use this 400 force. I need IJK. How much I'm moving in my R? I am moving 0.5 meters in plus Y direction, 0, 0. And my F2 that I arrive at is 400, and that's pointing towards plus Z direction. That's all I care about. So the first one, if you do the math, you're going to get minus 600 K units of Newton meters. The second one, you're going to get 200 I Newton meters. So what the problem asking, resultant couple moment, is going to be MR, addition of those two vectors together. It's minus 600 K Newton meters. Thank you.